Hi, welcome to part 2 of your lesson on exponential functions. We were looking at all these kinds of functions in the last video, and we're just going to wrap up with a few more problems. This is the problem we ended on, and main thing was you know how to graph a transformed exponential function, you know how to find different parts of it like intercepts and asymptotes, you know what the domain and range are, and then you also know how to solve using your calculator. It gave you an equation here to solve, and the way to solve it was to graph both equations and find the intercept. So let's continue from there. The next problem is here. It's talking about the value of a boat, and it says the value of the boat can be modeled with this function, and x is the number of years since the boat was manufactured. So let's find out the value of the boat when it was brand new. Well, brand new in this scenario means at time 0, right? Because x is the number of years since the boat was manufactured. Brand new means no years have passed. Like it's this moment in time, no time has passed yet. So 0 is the value you put in for x. No years have passed. If you put 0 in there, you get a value of 20,000 because this turns to 1 and we're just left with 20,000. So in other words, when you look at this exponential equation here, this multiplier in front is like our y-intercept value right here. So 20,000, because this is in thousands, it says. That's the value of the boat in the beginning. Let's try B. What's the value of the boat when it was 3 years old? Okay, this time you're putting a value of 3 for x, right? So x is 3 now. Multiply, solve, and you get this value here. And it says give your answer to the nearest pound. So this is 12,282 pounds. And you can round that to 82.5 pounds, so you round it to 283. So 12,283 pounds. Notice that this power here is a value this base is a value below 1, therefore it's actually exponential decay, and it's making the value go down. That makes sense. Okay, C. Use your GDC to estimate when the value of the boat will be worth half its original value. So think about how you can graph that and think about what the half means. Okay, in this case, here's a graph. Here's the graph of the function we have for the value of the boat. It's graphed here in green. And we're looking for when is the boat half its value. Well, the half its original value, we know the original was 20,000, so half will be 10,000. So notice a line y equals 10 is graphed here because basically that represents the halfway mark in its value. So if you can find the intersection there, that's our answer. And here it says 4.27 years. Let's see if we can get that on our calculator. Okay, so I'm going to turn it on, and I'm going to clear my previous graph. Go to y equals, clear that. Clear that. I'm going to go up here and I'm going to enter our function. In this case, our function is 20 times 0.85 to the x power. So there's our function. And I want to graph that together with the line y equals 10, because that's the value we're looking for, the 10,000, half its value, and graph that. Let's see what we get. Takes a little time here, but it should appear soon, hopefully. There's the decreasing function, the exponential decay function. There's that. Notice it's totally out of the window here. I mean, you can barely see it. So I'm going to change the window so I can see closer to that intersection. So I'm going to press window, and I'm going to make, let's see, I needed the y value to be higher. So the y max I'll make 20, and the x max was okay. Let's try again, graph. So the decay function should be more clear now. So there it is. And then we're going to see the y equals 10 line right there. And we're looking for that value there, because that value there will give us an x value, which means how many years will pass until its value is 10,000, right? So let's do second calc. I'm going to look for the intersect again. And as you remember from last time, it asks you first curve and then second curve. Basically, if you had graphed like 10 curves at once here, it would want to know, well, you want the intersect of which 2 out of the 10. So you have to select the 2. But in this case, we only have 2 graphs. So first curve should already be flashing on one of the functions. There, I'm moving arrow. There it is. It's flashing on that one. So that's the first function. And then second curve, now it's flashing on this one. So that is the second curve I'm trying to find the intersection of. And then it says guess. And guess, I didn't explain it clearly before, but guess just means bring me as close as you can to the intersection you want to find. Because sometimes when 2 graphs collide, they actually intersect at 2 points. Like, for example, a parabola and a parabola, or a parabola and a line can meet at 2 points. So this guess thing means, well, tell me which of the intersection points you want me to calculate. So I'm going to put it close to that one, enter, and it will calculate that intersection for me, and it gives it to me right here. So 4.26 is our x value, y is 10. Well, it should be because we know we have that line. So 4.26, I think it was rounded, 4.27. So it takes that much time for the value to become half of what it was. Okay, great. So now a special function. So let's end this part 2 video with a very special function, and it's something interesting, and we often see this in exponential functions. Let's take a look. So this is our special function. And let's begin with this table. Let's fill in some values. So how about you tell me the values of when x equals 1, 2, 3. What happens when x is 1, 2, or 3? When you put those values in here, what do you get? So let's check that, and that. Double check your work. Basically, you're just putting a 1 here, and then a 2 here, 2 here, and then a 3 here, 3 here. Now, try to fill in all the way down, see what happens. Let's just say fill it all in, but tell me in terms of the next question in this video, tell me what the value is when x becomes 100,000. Well, if you keep following the values down, you'll see they keep changing, but eventually, look, in the beginning they're changing from 2, 2.25, 2.37, 2.4, but then eventually they reach 2.7, 2.7, and then it's just kind of the same. So it's kind of reaching a plateau, a value that it's nearing and not changing so much, even as these values change a lot. So that's the value there. Graphing that, if you graph the function, it would look like this, right? First it begins at let's see, when x is 1, y is 2. When x is 2, y is 2.25, and so on. But then it doesn't rise that much, right? When x is 10, it's still only like 2.5, and then it doesn't rise very much. Like I said, these are approaching a certain value. It's not rising quickly after that, just rising slowly and getting close to 2.71. So that's the graph. Now, you may remember we talked about limits when we did calculus. We can think of this in terms of limits as well. And this means here the limit as x approaches infinity. So as these x values near infinity, right, as these x values become infinitely large, what happens to the function? Well, we can already see it happening here, right? As the x values become closer to infinity, the y values plateau at 2.718, it looks like, right? So the limit of this function as x goes to infinity is basically that asymptote that this thing is approaching. It's approaching its asymptote. There's like a limit there. It's not going to surpass that value, and that value is 2.718, roughly. I mean, yes, it's a little bit beyond it right here. But anyway, it's roughly right around there. So that's our limit. And that is the equation of that line there, roughly, right? Okay, so that leads us to a very important value. That number, that value we just found, is called Euler's number. We often call it E. It is an irrational number like pi and many others. It's this key number in mathematics, and it is approximated to this value here. So again, we had that graph. We saw that when we had that function, that special function, it reached that value. So that is that graph. But now what if we take this function and make it an exponential function? Because we've been talking about exponential functions. So we have y equals the base e to the power x. So we already looked at exponential functions like 2 to the power x, 3 to the power x, but now this is e to the power x, which means 2.71 to the power x, which is just another exponential function, and that one is going to look like this blue one here. Just like y equals 2 to the x was an exponential growth function, so is this. This is an exponential growth function as well. It's 2.718 to the power x, so it looks like that. But the interesting thing about this one in particular is this, and this is where it's going to bring us back to calculus soon. So like pi, it says e is an approximation of an infinite decimal. It is between 2 and 3, and it is around this value. We already saw that. And e to the x, so this power function, has the property that e to the x has a gradient, right, which means slope of 1 at 0, 1. So at this point right here, at 0, 1, the slope, which is represented by this tangent or red line here, has exact slope of 1. Okay, so as you remember, slope changes at each point on a graph, and we use a derivative to find that slope. So there's all kinds of slopes along that blue curve, which is this function, but exactly at that point, the slope is exactly 1. So that's an interesting property, because the power function y equals 2 to the power x would have a very different slope at that point. Or the power function y equals 3 to the power x would also have a different slope. But this one, only this one, this specific value of 2.718, has the exact slope of 1. Why? Why does that happen? All kinds of interesting things to think about. But we'll get back to it again soon when we look at this from the lens of calculus. So exciting stuff. That's it for this lesson. We'll see you later.